So in our lab, we study mutation rate evolution in basically using in microbes, using E. coli and yeast as model organisms. And basically the idea is that asexual organisms, because they have complete linkage, if the beneficial mutation supply rate is high, you can basically substitute a high mutation rate. So a mutated allele that rises in a population of asexual organisms can increase in frequency if it becomes linked with a beneficial mutation. So since if a beneficial mutation arises, it will always remain linked to its background in an asexual population. The mutated allele can increase in frequency because by virtue of it being linked to that beneficial mutation. So I'm interested in what happens to beneficial mutations that arise in populations that have extremely high mutation rates. And so that's what we call hypermutable asexual populations. So what does hypermutable mean? In further terms, or for the purpose of my research, hypermutable implies asexual populations that have mutation rates that are sort of 4,000 to 5,000 fold higher than wild type E. coli. So we've constructed strains in the lab that are E. coli K12 strains that have two mutated alleles. So they have been knocked out for function of mutation mismatch repair and DNA proofreading. And so by virtue of those functions being knocked out, they have a mutation rate that is sort of 4,500 fold higher than wild type E. coli mutation rate. So when we, if you think about theoretically, if you have a really high mutation rate, then you have an elevated rate of beneficial mutations, and you have an elevated rate of deleterious mutations. But in hypermutable asexual populations, basically what happens is over the short term, they can supplant populations that have lower mutation rates because of the increased supply of beneficial mutations. But over the long range, what we expect theoretically and what we've seen from simulations is that the fitness will actually decline over the long term. So I have some simulation results here. So NE is effective population size here. What I'm graphing is on the y-axis fitness, and on the x-axis we have time in generations. So if you look at it, over time, actually in generations, the fitness tends to decline in populations that have extremely high mutation rates. And this is sort of the prediction that correlates with theory as well. So these are simulations that I've done myself. And going back to my question, since I'm interested in adaptation and how adaptation proceeds in populations, I'm interested in what happens to beneficial mutations that arise in these populations. So basically, since the mutation rate is very high, we know for sure that beneficial mutations are arising. They're accessible, but they are not able to spread, or for some reason are not able to increase in frequency in these populations. So going back to classical theory, the prediction, J.B.S. Haldane derived the result for what's the probability of fixation of a beneficial mutation that arises in a population uninhibited by any other competing beneficial mutations or deleterious mutations. So if there's no other mutation, it's only that one beneficial mutation that's trying to spread in the population, it's going to be 2x. So that's classical theory. And there are some assumptions. The assumptions are there's no other beneficial or deleterious mutations. The population is large and of constant size, and the offspring number is small distributed. So basically, if you think about beneficial mutations in a population, you can picture sort of two scenarios. A beneficial mutation may arise spontaneously, so that its starting frequency is 1 over n, where n is the size of the population. Or the other scenario is that because of a change in environment, a mutation that was previously neutral or deleterious has now become beneficial, in which case its starting frequency may be much larger than 1 over n. So in the first case, the probability of fixation is comparable to the classical result that I just showed you, so it's 2s. And in the second case, the probability of fixation is in fact much closer to 1 because it's very less likely to be lost. All right, so let's consider the first case. So these are simulation results that I have got from my simulations. So basically the simulation is a population of asexual organisms and the population size here is, the effective population size here is 1,000 individuals. And the simulation contains only deleterious mutations. So remember that Haldane's result applies to a population that has no deleterious or beneficial mutations. But this simulation contains deleterious mutations since I'm interested in hypermutable populations. And what I'm graphing here is the chance of fixation, and basically chance of fixation of a beneficial mutation that has been seeded into the population. So that is the only beneficial mutation. There's no other beneficial mutation that's competing with that one. So it's the only thing that is impeding its progress is deleterious mutations. And the different lines here represent the black dashed line. That is the 2S expectation. Because on the x-axis we have different mutations of different benefits. So the S values there are different S values for different beneficial mutations. And so the black line represents sort of the 2S expectation for that S value, and the other three lines represent different genomic deleterious mutation rates. So basically that is number of deleterious mutations per generation per genome. So 0.45 is around 2,000-fold higher than wild-type E. coli. 0.9 is around 4,500-fold higher than wild-type E. coli, and 2.7 is I guess around 6,000 to 8,000-fold higher than wild-type E. coli. So you can see that as you, yes, this was the pointer, as you increase the sort of deleterious mutation rate, the line sort of deviates more and more from the 2S expectation. So we can see a clear effect of the rate of deleterious mutations on the sort of probability of fixation of this beneficial mutation that's being seeded in. And a reason why it's deviating even more here is because the classical expectation 2S applies to smaller values of S. It's an approximation. The actual formulae is different at higher values of S. So again, since the other scenario I discussed was what happens when frequency that you start with is much greater than 1 over n. So this is sort of simulations that show what happens when starting frequency is much greater than 1 over n. In this case, since the probability of fixation will be 1 minus probability of loss, the probability of loss will be 1 minus 2s raised to the n, where n is the starting size, and 1 minus that number will be a very small, this number will be very small, so this is approximately 1, so the probability of fixation is approximately 1. And so in this case as well, we see that the probability of fixation is actually much lower. It's actually 0.45 when you're starting at, so in this case, the starting size is around 5%. So we're starting at 500 individuals in a population which is 10,000 individuals total. So that's 5% starting size, but you're still seeing a much lower rate of fixation than you expect. So the reason we think this happens, and the reason we think this happens is because in a population that's constant in size, if you have a mutation that sort of, beneficial mutation that sort of appears, it's going to start to expand in size, so it's going to start to grow in size. And what happens in an asexual population when it's growing from, when it's at a smaller size, is it suffers from this phenomenon that we call Muller's ratchet, right? So this phenomenon is basically the stochastic loss of the best genotype that occurs. And the rate of Muller's ratchet depends on both the mutation rate and the size of the lineage. So since this beneficial lineage that arises is going to be much smaller in size as compared to the rest of the population, it's going to suffer what we call an accelerated Muller's ratchet. So the Muller's ratchet is going to operate much faster in this sort of small lineage. And that's why we think that there's a sort of frequency dependence or sort of starting lineage size dependence when it comes to the fate of beneficial mutations in very high mutation rate populations. So basically the idea is that beneficial lineage must accumulate deleterious mutations at a rate lower than the average deleterious mutation rate accumulation rate in order to persist in this population that is hypermutable. And therefore, as lineage size decreases, the probability of fixation will tend to go to 0. In order to show you this lineage size effect, I have some simulation results here that are more compelling, I guess. So this is a simulation of a population that at varying population sizes. And basically what's happening here is that the focal mutation or the beneficial mutation that I wish to track is being seeded at the exact same frequency in 3 different population sizes, but the same frequency implies different lineage sizes at different population sizes. So here, the population size here is 2,000 individuals, and the lineage starts at 5%, so that's 100 individuals that are beneficial. And the green line, the red line is 20,000. The total population size is 20,000 individuals, and as far as the beneficial lineage goes, 5% of that is 1,000 individuals, and the green line is 200,000 individuals in total, but the number of beneficial mutants is 10,000. So as the lineage size increases, you can see that the fates or the evolutionary dynamics of these three in these three populations is completely different. So here, the beneficial mutation sort of loses out and cannot fix. Here it sort of goes into a higher frequency and then loses out, and here it sort of tends to go to fixation. And that's because we think that there's sort of lineage size dependence because of that phenomenon of accelerated Muller's ratchet that I just described to you. And we also tend to call the accelerated Muller's ratchet something like private Muller's ratchet because it's private to that particular lineage that is expanding in the population. This graph also shows you that sort of frequency dependence that I just described. And here we have a sort of smaller effective population size, NE, and SB is the benefit of the mutation that is being seeded into the population. And what's happening here is the green line is sort of showing a population that has a mutation rate that is much closer to wild type E. coli mutation rate. And the blue line is showing a population that has this sort of double mutator or 4,500-fold higher than wild type mutation rate that I've discussed before. And so basically what's happening here is I'm seeding in that 5% benefit mutation into both of these populations, but starting at different frequencies. So you can see starting from 0.05 to 0.5, and as you can see that in the green population, that is the lower mutational population, there seems to be no sort of frequency dependence. So as long as you're starting at something like 0.5%, you're pretty much going to fixation. Your chance of fixation is pretty much 100%. But when you are at the higher mutation rate, there's a sort of frequency dependence starting so between 0.05 and sort of, I guess, up to 0.4. So between 5% and 40%, anywhere there, between there, your probability of fixation is not 100%. So you're not 100% likely to fix starting anywhere between those 2 points. And the reason for this is the mechanism that I described to you before, which is this sort of private Muller's ratchet, accelerated Muller's ratchet, and we think is operating in these populations. So basically we think that this process arises because of sort of asymmetry in the way deleterious mutations accumulate in lineages in the population. So if deleterious mutations accumulate as a sort of Poisson process, then every individual in the population can be considered as a lineage, and every individual accumulates deleterious mutations at a different rate. So as long as this rate is asymmetric, we can expect Muller's ratchet to operate at different speeds in different lineages. And so I thought of, maybe if you take this process out, what will happen is we'll come back, the probability of fixation will come back to sort of 2S expectation. And so as an effective control, I did simulations where I calculated the empirically calculated the rate of fitness decline over time, and then imposed a constant fitness decline, that exact fitness decline, to every individual in the population. And so what happens then is if you do that, basically you see, so this green line is the 2S expectation, the blue line is what we see from our previous simulation results, which is if the deleterious mutations are encoded as a Poisson process, and the red line is what happens if you encode deleterious mutations, if you encode a constant decline in fitness every generation. So if you do that, you see that you come back, you come very close to the 2S expectation, and so imposing this control puts you back to that 2S expectation. And the blue line is still the Poisson process that I mentioned before. So that's the end of my talk. So just to mention this again, so this is all computer simulations, and now we've developed an actual experimental model to test this idea, and we've actually done some preliminary experiments that I'm not discussing here, but I would be happy to discuss if you want to talk to me after the talk, after the session is over some beer. And just my last slide is just acknowledgements to thank everyone who's been a part of this project. My advisor is Dr. Sniegowski, University of Pennsylvania. I've been working with Dr. Gerrish at Los Alamos, and Dr. Untitled.
Unfortunately, we have no time for questions, so